Well, I don't quite know how to follow that up, except to say there was some similarity. Or that it's very hard to open parachutes at high altitude. Yeah, you'll see the. What do I have to press to get the screen up? I don't remember.
Probably you blew FN.
FN
5, try that. F1.
Oh, I haven't. You know what? I haven't put the VGA in.
That helps.
Where is that? Sorry. The other end of this.
There.
Just check.
Is it?
Before we bring that up.
Just that where you come back to on screen, I'll go to my Instagram.
Just checking in here because I
All
have.
you need is to confirm electronic connection.
There we go. Okay. There we go. Super. Okay. Let's go back to the start. You've seen enough pictures of balloons launching. Let's find something else to start on. So I did this at Cosmica. Some of you may have seen, some of you went to that, I understand it. My name is Oliver DePye and I do work for the Medical Research Council in North London, but you heard me say that because this is entirely off-piste. I think what that makes is a physicist or anything like that. I'm a molecular biologist, but for many years I've had an interest in what we now refer to as AFI. Go back to before astrobiology emerged as a discipline in the mid-1990s. What I'm going to describe to you today is a sort of astrobiological desert road trip of effectively enthusiastic amateurs. We knew what we were doing within our various disciplines, but we were not working for anybody. In fact, I don't need to elaborate on that because that's what most of you do when you fly your balloons, effectively for pleasure as enthusiasts. But what we were trying to do is try and do molecular biology at high altitude to look for life. I'll take you through the reasons for that in a minute. And so, as well as actually trying to build a balloon and a payload to do this, we were also actually doing exactly the equivalent of taking, building something in your shed, but actually trying to do molecular biology in a shed, or in my case, actually on a old baby changer that my daughter's grown out of, but it's in the corner of my bedroom. We have a little sort of mini lab and workshop there. So we sold it away and sort of try and come up with a home-built astrobiology payload. So that's what I'm about to describe to you. And this, by the way, is a book that describes this emerging movement of people doing molecular biology as a hobby. It's exactly the same way you would solder things in your bedroom or in your shed or whatever. People are starting to do actual molecular biology and biochemistry at home because the reagents are available and safe and cheap enough to do that. And I'll show you our approach to that in a minute. And we were funded by the National Endowment for Science and Technology and the Arts, and that was some fun we had in some downtime in the desert, which I'm going to describe to you with a time-lapse camera. Now, at that time, Leicester used to fund programs like the Crucible program, which was entirely centred around building unusual collaborations, because there is this idea that if you do build an extremely unusual collaboration between disparate people, scientists and artists, physicists and architects and molecular biologists and whatever, that you get a sort of brainstorming effect And when people are outside their silos, they will come up with novel ideas. And if you build an environment where you can discuss those things openly, without ridicule, people come up with new ideas. And that was the scheme to bring us all together. And then there was project money you could bid for. It's not there anymore, unfortunately. And I was trying to come up with a sort of mainstream. My day job is actually trying to build laboratory robots to automate molecular biology in the lab. And I wanted to do something like that, and somebody said to me, we're just not interested, we're architects, that doesn't interest us. If you could think of one thing you'd really like to do, what would it be? And I said, I'd like to do astrobiology. I was an intern at NASA for a while, about 10 years ago, and actually that really excited. It excites you, you're all in a sort of similar field of space research or near space research, and I think it does have this sort of visceral interest that people forget, and very rapidly we managed to make a project out of it. And the actual project I came up with, because I was aware of some high altitude balloon groups in the States who worked with my former colleagues at NASA, was a balloon-borne bioprospecting project looking for life in the high atmosphere. And various people have said they found it. I, as a molecular biologist, I have my doubts, and I wanted to build a payload that we could go and see what we'd found. I worked with a group of colleagues. There's a photo of them later. A lot of these pictures are taken from blurb book built by one of my colleagues as well. You might see, must be copied in various photos. That's from her proof. She's fine with it. You can buy that book if you've got £38. So, balloon project, relatively easy to do, as you all know. This is something you probably know about. This one that I got off the internet. And the red line is temperature. Pressure has got chopped off on the side, but there's pressure up the side. We're down here in this filthy bit of the troposphere, so you'd expect to find life there. You go up, it's extremely cold until you get to the stratospores, and then we're flying our balloons up here. And wherever people look, they seem to claim they found spores or bugs or whatever. I have my doubts. As a physical process to get stuff into the high atmosphere, there's certain air currents that can do it, a volcano can do it, forest fires can do it. So there's certainly sources of convection and other natural currents that could carry, tiny particles, spores, or bacteria into the atmosphere. So from that point of view, it's quite possible to imagine that it gets up there. Whether anything lives there is a different matter. It might just go into hibernation and drown. Even that would be interesting, of course, because it's a possible way that disease can be spread across the world. And there's certain evidence, particularly with, say, foot and mouth, that could drift hundreds and hundreds of miles. And whether things could drift further in the high atmosphere, I don't know. If you can go and find it and prove you did it in a very valid, scientifically vigorous way, then you can say, look, I really did find something that looks like a pathogenic bacteria at altitude. I think this is a disease vector. Craig Venter, by the way, the guy who sequenced the human genome, amongst other things, he was very busy taking air samples at sort of ground level and seeing if there was a lot of bacteria in cloud and so on. I haven't heard anything further about that. Maybe he didn't find anything particularly useful, but he certainly had a similar approach lower down. A very vigorous air sampler guy. And maybe some of you can build a balloon from one day. Okay. No. I'm on an iPad, just telling you something that in the break. Right. I obviously whittled onto you all. Okay. The other thing about this graph is it gets close to or above freezing over here. Very cold in the tropopause, but not too bad over here. And to my mind, there's a sort of sweet spot around 100,000 feet or so, when the temperature is above freezing for some of the time, and the pressure is enough that although the boiling point of water is very low at high altitude, it is not, it's 3 or 4 degrees. So you can have liquid water persisting in terms of both pressure and temperature at high altitude, and any astrobiologist will tell you that nearly wherever you ever find liquid water, you find life. So then there's a possibility, and you could make an argument that there's little flecks of dust, something like that, with some water on it, bacteria living on it, and most astrobiologists would accept that as a perfectly reasonable premise. And there is, for instance, talk that even in the atmosphere of Venus, There's some bits of Venus where the temperature isn't too bad, and there's even some moisture in the clouds. You can have bacteria in the clouds of Venus, although almost certainly not on the surface. So clouds and atmospheres as habitats is an emerging theme, and this is what we were looking at. Around about 100,000 feet, that's what I had in mind. Now, the next graph is the vapor pressure of water against temperature. That's in Tor. What's a Tor? I can never remember. Here we are, around here, 100 degrees Celsius, and that's the boiling point of water, right? That's where it exceeds, the vapor pressure of the water exceeds the pressure of the atmosphere, and it just starts boiling on. But that is, of course, not the linear graph. Now, the reason I've shown you this is if you're looking for something, if you're looking for Amanda Knox's DNA or something like that, you carry out something called polymerase chain reaction. I expect none of you know what that is, but it amplifies up. He knows. We'll come to you later. Who are you?
He's a doctor.
Oh, super. I'll just look at you for the rest of the talk. Anyway, so we've got the polymerase chain reaction. I won't take you through that, but one of the things that you need to do for the polymerase chain reaction is you need to cycle it repeatedly to actually up to a very high temperature, about 94 degrees centigrade. So to do that, I would need to build some sort of pressure vessel, applied altitude that can hold a full atmosphere of pressure. And I need like a Peltier element or something that could repeatedly cycle up to 94 degrees, then it goes to 72 degrees, and then it goes to 60 degrees, and it repeats this over and over again. And they're not very expensive in the lab anymore, but they take up several thousand watts of power, and they're quite heavy, and I need one atmosphere. I really didn't think that was a useful way to do it. I might actually, if I did it over again, I might consider it, because now the cheapest PCR enzymes are out of patent. They're incredibly cheap. They're down to a few pence per reaction. So there's something a biohacker might do. Many biohackers have tried to build their own PCR machines. But I thought that was not a good idea. The other thing that's not a good idea about it is, I've got bacteria or whatever that spend their lives at 100,000 feet at maybe 10 millibars, and I'm suddenly insisting that they partake in an experiment at a far higher pressure, and that's not the environment they're used to. Am I going to kill them all dead as soon as I pressurize them before I even get to do my experiments? So what could I do as an alternative to PCR at these high pressures? And it's not a linear scale. And down here, we get to sort of 37 degrees centigrade, which is the temperature we live at, and you can have really very low pressure. 20 millibars is enough to stop water boiling. So that's, I thought, the where to aim at. And of course, when the human being replicates the DNA, I have a daughter, some DNA replication must have been involved in that. We don't have beta cells up to 94 degrees centigrade. We have enzymes that do it for us, and in a linear way at 37 degrees. And we can now buy those from a company called TwistDX. And TwistDX has come up with an enzyme that just functions at that temperature and nothing else. And you mix the stuff together you want, and it replicates DNA. So that's where we started designing our experiment around. And so there's every living cell that anybody's so far found has a particular type of DNA called 16S RNA. That's like the benchmark that you look at to detect whether life is there. So we amplified that. Except for James, you guys aren't that interested in the detail. But that's not so clear. Maybe you can look at my laptop later, some of you. But this is what I built in a great hurry for a crucible. And it was basically made of four blades, so to speak, made up of 4 perforated aluminium sheets. And each sheet, these had ice blocks, commercial, camper ice blocks. And the reason for that is that going up it would get very, very cold. So if I had a lot of unfrozen ice blocks in that would be thermal mass, and they would keep the temperature above freezing, so I wouldn't freeze all my reagents and chemicals. That was the plan anyway. And then they would keep it cool on the way down, because they would have frozen solid at high altitude, and they would keep it relatively cool on the way down. And the other problem was, if we were operating in a desert environment, it would be really hot when we were sitting on the desert when it came down. I haven't got to that bit. I'll tell you where we launched later. 4 blades, each blade had an ice block in, and these syringes firing down into this reaction vessel here. You can see the tubing. And these springs are shape memory alloy actuators. This is all linear motion. I didn't want stepper drivers or stepper motors or anything, so what I used is these shape memory alloys. So you put about 3 amps through these momentarily and they'll contract with about 4 newtons of force. So I really love these. But then of course I have now built a balloon payload which needed momentarily to be able to switch 2 or 3 amps. So there's the reaction vessel. That was a fluorimeter, because basically what I'd done is I'd incorporated a dye that bounds to amplified DNA. So as the DNA got amplified, if there was any there, you would get a fluorescent signal. If you beamed the right light into it, it would fluoresce at a different wavelength. I would be able to see if there was any DNA amplified in this reaction chamber I made. So 4 syringes firing into that. I can tell you about what exactly was in that later. And I had an air sample. I had a great big syringe that sucked air in and bubbled it through the reaction chamber to see what was happening. So that's like my basic approach. 4 biochemicals that needed to be mixed in series using shape memory alloy. Down here, it's not in this picture, there was a water heater with a pump in it, and actually and then there was coils of tubing around out to keep that at the right temperature. And some of you may have seen me discussing how to try and sample air, keep everything sterile on the way up and then only sample it at altitude. I don't quite know how I've worked out how to do it. One way I was thinking quartz window and a UVC LED and try and sterilise it that way, and I would have sampled around the edge of that, something like that. That's kind of what I was thinking, but that UVC LED was a very expensive cost, so I'm not sure that's going to go. But there we got it, the 4 ice blocks and the syringes, the reaction chamber, and the UVC, quartz, sterile sampling quartz, so you get an idea of what it looked like. And the whole thing was in a tube. And this rather elongated, that's about 37 centimetres by the way, that rather elongated design is because, as well as this balloon opportunity, this was through my former colleagues at NASA, they'd also given us a rocket flight opportunity. So we were trying to fly something to similar altitudes by 2 completely different methods, and that we found that an irresistible challenge. And so we flew over to America last August, and we found ourselves in a garage in San Jose with all sorts of strange and wonderful things in it, because just like you guys, there's a thriving amateur rocketry movement in the States as well. Being the States, everything's bigger and better, and so basically this group called the Rocket Mavericks, who work out of California, they're a mixture of aerospace engineers and sort of .com people and so on. They've got a lot of money and expertise, and they're building these very large semi-pro rockets. I'll show you a key example of that later. So this is the kind of expertise we had available to us, if we asked nicely, although they were very distracted getting the rocket ready at the same time. So anyway, that was the environment we were working in. And then we drove out to the Black Rock Desert in the middle of Nevada, and the advantage of the Black Rock Desert is that you don't need to file the low term if you don't want to. We did, because it was sort of considered polite, because my Rocket Mavericks colleagues were flying these enormous rockets and so on. We did need FAA clearance, but so they wanted to do a low time for everything. But in theory, if you drive out there, you can just launch it. This is where they have the Burning Man Festival and so on. So as a biologist, I began to think, well, this isn't a particularly sterile desert. I mean, it wasn't going on then, but God knows what. We did do some background counts. The air you're breathing now has probably got about 300. I can't wait for my iPad. Excuse me. The air you're breathing now probably has about 300, 400 bacteria that you can grow on a petri dish per cubic metre of air. And the air out there was at about 20, 25. It's not particularly sterile. There's a town over there. There's a gold mine over here. There's hydrothermal vents and railway and roads around it. It's a big, big desert, but it's really things that are not sterile. And so it's certainly not a particularly sterile place. So when you're assembling a balloon, this is the absolute thing I'll go on and on about, especially on the discussion group, is that you're assembling a balloon and effectively it's being coated with bacteria the whole time while you launch it. And you've always got the wonder if that's what you detected. Somebody flew a U-2 plane, spy plane, and they said, look, we found bacteria on our sample plate. And I said, well, how do you know you didn't take that with you? Your sample plate was sterile, your deployment mechanism of sterile, or you're actually sampling bacteria that just come off the cockpit window or off the the wheel well or whatever. Very hard to do. Maybe we can discuss that later. At least, we launched in a slightly more sterile environment than normal in the middle of a fairly desolate area, although every year, whatever it is, 40,000 people turn up to burning land. So it's not that sterile. But it was extremely beautiful at night. Again, you can't appreciate this with the background light, but we did a lot of mucking around, time lapse in the light, although we were normally a bit like Ed, completely shattered by that point, just fell asleep. And that gives you an idea of the balloon, of the sort of payload we put together. We rented an RV and took whatever tools we could with us. So there's the payload again, and we've got a massive wiring, capable of high-out wiring. Some of the petting detail now, a memory foam which we use to insulate things. And the bit that you're probably most interested in is this bit. That bit is a great big chunk of solid state relays with a 3 amp, turning the 3 amps on and off to go through here. And this is a PC104 stack. The reason I did use the PC104 format as a complete amateur was that the people who I was flying with, who were doing the balloon for us, before NASA cut off their funding, which I'll describe later, but they had one balloon left and they were very kind and they gave it to us because they wanted to make one more flight. They'd been flying PC104 cards, so I'd gone down this route of thinking I had to use PC104 cards so I could prove like I could play with the big boys and say, look, I've got PC104 cards too. And because they, the standard is that they're all compatible with each other, and CubeSats are built using that, you're always at a pinch saying, maybe we can turn it into a CubeSat later. These balloon payload people always had an eye on turning them into CubeSats. Some of these were considered to be basically CubeSats on a balloon. So, this for car that we've got a supply P4 analog to digital. I also used to turn the relays on and off, and you downloaded the relevant C libraries. It was all meant to work. I had a lot of trouble programming it. I don't think I'd do it this way again, but it is one way people can do it. Now, some bits of this still work. This bit doesn't. That was the actual, I've taken it out of the box. I was going to show it to you as debris, but I think it's interesting to compare in sort of size and power with what Ed and some of the other people described. So it's a fully formed little computer. I think it's got about 64 megs. It runs Linux. It's got an ARM processor. It had an SD card slot, which I wish I'd used, so I had some sort of disaster recovery. You can stack all the other things on it. So it's quite a fully formed computer. You could run a monitor off it and so on. I think the bare board would be a couple of £100. I'll pass it around later. If anybody can work out why it doesn't work anymore and get it fixed, I'd be extremely grateful. I don't think I'd do it that way again because it's just too much of a liability and it's too complicated to program.
How much current was it using?
This?
Yeah.
Very little. This one, very little. But I think the power supply was running on about 1 time.
Okay, that's a lot by balloon standards.
I know it's a lot by balloon standards, but the whole thing was pretty big. I mean, you could, the greatest way would be on the ice, but you need, if you have a maybe make it very small. That's why I try to make it much smaller. But this is what, in a panic, when I was given like 2 months' notice of having a rocket flight, I built in my bedroom. It's not necessarily perfect.
Why? Sorry, I misunderstood earlier. Why do you have 4 ice packs?
Because there was 4 syringes and each syringe was an extra ice pack.
What different channels for?
Right, 4 reagents. The first reagent is a lysis reagent, basically a detergent, which we bubbled the air through. And that's what you call an impinger. You usually, to catch stuff, you bubble it through water or something when you're doing an air sample. So that would break open anything we saw, including spores, and use the DNA out. The second one was the TRIS-DX. What we then found, though, the problem was you set up a PCR with what's known as primers, little bits of DNA that flank the bit you want, and they were causing a false signal. So the third syringe was something that digested primers, and then the 4th one was the dye, because the dye interfered with the previous 3, so you have to do that was 3 syringes. I don't think I can get it much better than that, unless somebody had a die that didn't bind the primus. But I haven't got any money there, so I can't try it again. But that was like my basic 4 syringe method. And I challenge any biohacker, without ego, to come up with something better. So that's what we flew, and we had, this power supply. That was quite neat. I had the PT104 stack. It's a relatively big format, less people. What I might do if I did it all over again, my particular approach would probably be to have each of these or bunches of these controlled by microcontroller, something like a pickaxe, all feeding back on a serial link saying I'm doing this, do you want me to do anything else, and so on, because it's like a pickaxe can take back up? Yeah. Now there's a good picture of blue, you like that. So any pickaxe can output serial and so on. I might have just one of these, the cheapest I can find, to take all the serial feeds, because these multiple serial ports, in my view, is always a problem, but with these I don't think it will be, because they tend to come with like 6 serial ports or 8 serial ports built in, and they're all interruptible as well. So this is the only thing, believe me, my life is full of being tortured by multiple serial ports. At the same time, in lab automation, this is the only thing I really trust to do it, because the little boards are dead to anything else. Anyway, so that's what we flew. And FAA regulations are that you can have up to 6 pounds in your payload. You can have up to 2 6-pound payloads. So you can have 12 pounds, but then you have 6 in any one box. There's box number 1 and box number 2. With a large loop of cable between them. That was maybe not quite within the spirit of the law. Pre-deployed balloon as normal, no cut down. That's the tracker payload, and in the States they do things quite differently to you guys, I think. What they did actually is they had like a Garmin GPS particular model where you can get some feed out of it, and then an APRS radio, and the two were linked together by a cable. So it's quite simple. There are 2 pieces of one handheld APRS and one handheld Garmin in a cable. No custom stuff really. Although they had to do quite a lot of repairs on the radio to get it working. And that basically chirps over the APRS waves the whole time. And then they had an offline version of Google Earth, and they were plotting where it was in real time on that. My payload, because we had uplink, actually I've been just given this Digi XT radio modem kit, 900 megahertz, and in the States you can go up to 1 watt. So I had a 1 watt 900 megahertz transmitter there, and it had a big remote controlled car battery as well. So it was a pretty heavy duty payload compared to what you guys did. But what the temptation of the radio modem is actually it's a Linux thing. So when it was working, you could talk to it over network and have like a Unix shell open up, Yeah. And then you had the radio modem, and you were doing the same thing. You could actually log into it and everything. And I just the temptation of that, particularly if you had a long flight or you wanted to upload new commands and so on. I thought I kind of found it irresistible. I still quite like to do it. I was talking to it in theory at 9600 board, but I had very bad comms on the balloon flight. Later on we found it was because of a broken antenna. It was just a whip antenna on the radio modem kit, and it was just very, very poor signal off that. And if we'd known, we could have probably got much better communication. So I didn't get that much science out of it. But I still got intermittent comms all the way up. When I talk about the C library being difficult and so on, what I couldn't get was any useful data out of it. When I tried to ask it what the pressure was and temperature was and so on, it just came back everything off scale. So I don't know whether it's hardware or software, whatever. It was disappointing, but it was a first flight. We could have fixed it all if we'd had more balloons. But that was the approach we took. What didn't quite work the first time. I have the balloon being launched if people want to see it. I'm sure you've seen lots of balloons launched. And the guy held his camera in the wrong rotation, so just lean over.
Very good.
Yeah. There's the cable between the two. And it's just a very, very clean launch. Black Rock is ringed by mountains, so they've done similar predictions to you to try and make sure it came down in the Black Rock. Then we would have been very happy. And they tried another flight the next day using somebody else doing it, didn't have enough helium, and that they ended up horribly tracking that.
Down your hands now.
But yeah, the infrastructure these guys had worked pretty well.
Pull your truck over for
And that was the only time driving around trying to chase it. that was the first time I appreciated what four-wheel drive cars really were for in that terrain. So at a fight of about 2 hours, we recovered it nicely. We saw it actually land in front of us because you can really put the pedal down and then actually on the plaza itself, on the player itself. And we recovered it in good order, except in telefold. So we didn't get the science out of that we wanted, but we did at least prove that the overall infrastructure worked. I had comms. Again, everything was off scale, so it was useless scientifically, but I did get a signal near its burst point from my side of the payload. And that's all I'm interested in, frankly, to trigger it. You know, I don't care if I only get half an hour or 60 minutes out of my side of it. I just need to be able to trigger it at the appropriate point. And I'm a passenger from then on. I'm always a passenger. I'm just relying on your guys. I'm very humble about it, what you guys can do for me, or what my colleagues in America can do for me, and then I'm a passenger. You track it, and I'll do whatever unreliable, wacky stuff. You know, PC 104 cars, whatever.
If you make it and insure it, then tracking it, that's an issue. As long as you insure it as well, that's an issue.
I don't think we had to insure it.
The other day you said, right,
There we didn't. I mean, it's a good point. It's a bit bigger than some. I wouldn't be so big the second time round. It was just literally, I didn't design it.
What was the total weight of the payload?
£9, I think. So that was about 3. The whole thing was okay. You know, it was in the regs in the end. Just everything. The full stack came in a bit less than I thought it would be, and so we were okay. I would have lost ice packs, so I needed to make the test flight. I would just not taken the full complement of ice packs. I don't know what temperature was at, but the ice packs came back completely frozen, which was good. And the water recirculating loop, although the heater wasn't on, I left the motor on this test, and the water came back. The pump had stopped, but there was still liquid water in the line. That would suggest to me it didn't freeze solid, that it did what I wanted. It kept it close to above freezing, and the pump probably stopped the water really. So yeah, I was relatively happy on that side of things. Now moving on, you know, so we fixed everything we need to fix. So we had this rocket launch coming up. That was the next exciting bit. And this is us with my team. I say my team, it was my idea, but from the moment we started going, it was absolutely a community of equals, although it was, you know, it was my name on the top of the graph. And here we are squeezing into the rocket. It's a quartz rocket. Yes, it's round quartz. It's radio transparent, but very tough tube. So the rocket's down this bit, and we've got these couplers between various bits, because just like what Ed just showed you, it's meant to split in half with a parachute coming out in between. And this is my bit of it. And we're squeezing the payload in there. That's Mel. She's an extremely competent electrobiologist. That's Rainbow Low and Ed, I think you've seen it, Ed Campion, that's it. They were 2 6-4ers who came out, they won a competition that came up with us, and they were extremely helpful. That's me, and that's Paul Shepherd, who's a sort of FEA expert for building design, fire antenna analysis expert. Originally we were going to 3D print the whole thing, because he does 3D printing, but in the eventuality we just didn't have time. We might do next time. But it turned out he to be extremely competent at C programming, electronics, things like that. So that's, you've got that, you know, molecular biology into astrobiology, and then sort of hardware electronics in that picture. That's how the team builds up. But actually, the day job titles completely outside those areas of expertise. And this was something that an artist colleague asked me to take, because artists tend to have a lot more fun than scientists do, I think, and they have much broader opportunity to use their enthusiasm and so on. They don't have to concentrate on their day job. Their day job is doing wonderful new artistic interventions in the world. So she was very interested. She's actually a very well-trained biochemist. Her name is Anna Dimitri, and she works out at the University of Brighton. And this was homoserine lactone, which is effectively a bacterial hormone. So bacteria is signaling to other bacteria with different species using variants of this chemical. And so she said, well, why don't you, if there is any, why don't you release some, if there are any bacteria at altitude, why don't you release some homoserine lactone at all in from your balloon, and that would be like saying take it to your leader. Just a little bit of whimsy, a little bit of fun. And NASA said, no, you can't do that. You can't release anything from balloons. Well, it's like, you know, every bacteria on Earth does this. No, so we sealed it up completely as a sort of silly regulations, and it was on there, but it couldn't be released. But that's the sort of thing. I mean, we laugh at it, but Anna and her colleagues are so interested in what we're doing. You know, you might end up doing quite an interesting project with them, and that's they're part the people helping you do it because they've got the expertise, and you get involved in the whole extra community people you wouldn't expect to. So I'm very happy to work with them. So that's us sliding it in. That's just a bit of there's the main sampling syringe that takes the air in, and these syringes next to it are effectively being used as clamp valves. They're pushing down on the tubing, and they're crimping it so you can take the air in and then shut it off, and then open up the other crimp and push the air into the main chamber and so on. So you keep pumping air in. And that's loading the rocket on the rail. So those of you who know your rockets, I think that was a P class, and you can only go up to K in the UK. Yeah. Well, do you like Zs or whatever?
No, I was just thinking we normally go up to 11. So.
Oh, there you go.
It doubles every time we go up.
Yeah. Yeah. Well, we went like a bat out of hell. I don't have a good video of that one.
Yeah, it's a couple of classes over what we've done.
It was a bit spoiled. Yeah. I thought we only went up to K. I'm glad to see that.
No. M's and N's.
So the whole team, the Rocket Mavericks team, is there, but I think it's too murky for me to give a name calls. I'm happy to show people that later. I just particularly like to thank Thomas Aitkenson, who's the head of Rocket Mavericks. Well, again, he's a community resource who helped me deal with this, and there's Rob Briody, who's their main engineer, extremely skilled. We helped me build on that. And there's the big red button. Because all rocket launchers ought to have a big red button, maybe balloon launchers ought to have one too. And I got to press it because I designed the payload. We've got a couple of other cameras, but there's most of them just launching pictures of you only see the rocket launcher a second, so I'm not going to play them all back to you. But that one, unfortunately, we lost the footage. But after the launch, everybody broke out manhugs. So Rocket Mavericks team was obviously the intense male bonding moment. Everybody was man hugging. I don't know if that happens on balloon launches, but yeah. That's quite fun. So that's what we had. So that one went up to about Mach 1.4, and it went up to about 28,000 feet. We were able to fit the balloon payload on another rocket I'll show you later, which would have gone much higher. But still, it's nice to test things out. And those Digi radio modems, I can really recommend them because this thing going up to 28,000 feet at Mach 1.4, this time round, again with just the whip aerial, we have absolutely custom, crystal clear comms, right? And I was seeing the Unix shell from the payload as I was logged into it, and it kept sampling out and I'm going to sleep and so on. Perfect. So we can discuss it later. That particular wavelength and modem is not available in Europe. They do have, what was it, a 653 kilohertz version at 350 milliamps or something, which might give us really quite a lot of range. And again, this idea that not just chirping back telemetry, you're actually interacting remotely. It's quite fun. I think it's something that might be worth trying. At least just trying it. They're not particularly expensive, those modems. Now, so we didn't have a tracker on this. We were just everybody looking to see where it came down. And I saw a little speck under what looked like an orange strip falling like this. And we went out and followed it with all the other people. What we found was, I had some timing for light relief. What we found was that the whole nose cone of the rocket snapped off, and the nose cone was buried about 70 centimetres into the ground. Not a good sign. We did a pose there because this bit looked okay, and I still had a thought when we take it out, I'll be able to get some samples out. But it was not to be. Sorry?
Where was the parachute?
Well, that's a good question. It's over here somewhere. What had happened was, and I'll show you what I've got there. What had happened was, the main parachute failed, and they had a backup parachute, and some got thrown on it. So it's wrapped up a bit because it's all spiky in places. So those of you who can't, I'll pass this round, be careful. For those of you who can't see what I'm holding, this is all that was left. It's still shedding bits now. And that was like what Ed had done. Really, that's what, I mean, from the barometer because on their flight computer, from the barometer on that, they reckon it hit the ground at about 600 miles an hour or something. And it buried itself, I'm going into metric now, which is naughty, it buried itself about 70 centimetres in the ground, and I did the sum, and that's about 2,000 G. And that's there. Now, I don't know, I'll pass this round as well, because I really am seriously interested if anybody knows how to repair it, although I suspect it's a multi-layer PCB. There's the nose cone of the rocket, and all this had some padding on it and so on. What I think did the most damage is that this, as it constantly in, it gave an immense wrench on the data cable, and if you look at that, you will see it's bent the pins on this right up, and it's bent the PCB a bit. And I haven't got it, but I actually sent this back and said, can you just tell me if any of these boards are salvageable? I know I've invalidated my warranty. They actually sent me a letter back saying, we can't repair it, but just out of interest, I've never seen anything we've ever built destroyed so completely, and I'd just like to know what you did to it. But, it certainly takes 8G. 8G Mark 1.4 is working fine. And I think, this was like an enormous airbag, and it was the cable wrench that did damage. Have a look at them, I'll pass those round. But that's not the end of the story. Well, it's the end of my story. I was extremely depressed by that point. Because even if it was flawed or too heavy or whatever, I could have come back and tried it, taken to bits and tried it on the ground and flown it and so on. And it's obviously extremely annoying. I never plugged the power in. Excuse me. It's obviously extremely annoying that it got to this. Now, however, the rocket lab hadn't finished at this point. What we got there is the flights, and these are sponsored by Sony, and these had downward-looking cameras. What you had here is you had, I think, there, a 1P class motor there, and so that's the temptation of sticking with these guys and working out BlackRock. That would go into space. You'd technically be in space. You'd be above the carbon layer. And so, I think it was probably foolish to try and build a payload that did both things. But you can see where the temptation came from. Now, I didn't have a particularly good video of my rocket launching. I do have.
16, 15, 14, 13, 12, 11, 10, 9, 6, 5, 4, 2, 1. Ignition. Oh my God.
Watch it. This is first stage going out in the way. And then second stage ignition. So that's quite a trick to pull off. The combustion chamber broke through on the side at the last moment and spiraled out. But they had a lot of fun doing that. Didn't quite work to plan, but it's not bad first start. However, I will admit to a certain schadenfreude because that was what they found afterwards. the technically minded, what had happened was when the first stage separated, the second stage separated, I think the mark shock from that interactive mark shock of the first stage, I think it ripped a panel off the parachute mechanism or something, so the parachute didn't open properly. So that's the P stage they found there. And then the second stage going off, the spin at the last moment, that parachute can come out clean.
2,000 newtons,
I don't know how much that one was, but that one, as you can see, That, in fact, I realised that that's another rocket somebody tried flying. The parachute didn't work on that one either. What happened to that one was the parachute cords, as it was tumbling, the parachute cords got stuck to the hop, and they gave up trying to dig that one out. The law within the player, you've got to leave it completely spotless as you found it. So the ritual, if you can't dig your rocket out, it's just too buried. You take whatever's sticking out the surface, and then you drink a swig of beer and you pour the beer into the crater as an offering to the player gods, and then you cover up the remains. They dug these ones out. You know, the parachute opening to rocketry at those speeds, I mean, as Ed has just taken you through, is extremely difficult. Because they're super solid for the balloon community so much, for the rocket people, they need to either get their parachute to come out at the exact moment when it's at the very top of its arc, and then it's on the way down, or you've got to have supersonic opening parachutes. So I think it's very close to what Ed was describing to you. It's not at all easy to do, but you know. Now I know that now, but I wouldn't have built a payload that I didn't mind losing. If I did it over again, one approach, for instance, is to build a disposable payload when you don't want to get it back. Because after all, I'm doing my TwistDX application in flight, and I either get a signal or I don't, and I'm radioing the signal back. So as soon as I have that signal, it would be nice to examine, but the science of it is done. So
you're doing that presumably either because it's going to come down like this and you won't get your sample back.
Yeah.
But also, if you say you want to do this on Mars, you can do it.
Yeah. But it would detect this makes certain options protection. I'm looking at the sixth signal. If they don't have to see them.
Why didn't you sample? I just was slightly confused about that. Why can't you take a sample from those answers and come back in?
Because everybody does that. And they say, look, I found something. And I look at the bacteria they found, like they find bacteria, I don't know about that.
Surely you've got the same problem with clean.
Yes, I have. Yes, I have. But at least if I can prove it's clean going up, and I'm not sampling, and I find something at altitude, there's no possibility of it being ground contamination.
So if you take a sample, say halfway up, nothing was there.
Yeah, that's what I've been.
Sample higher up, you can say, well, look, we weren't getting anything below.
That's exactly what I've been discussing recently on the web group.
Because PCR, I mean, if something's there, PCR will find like it will amping this up massively.
Yeah.
So you're going from one strip of DNA to billions.
In my PhD, I found something which I think I traced back to work being done in another laboratory next to the laboratory where they made the sample that they emailed to. They'd given to my boss 8 years previously. That's fine.
The intelligent method, you get one bit. That's massive.
It can definitely give you false positives. If it do the DNA of a known sex abuser who is in the area at the time and doesn't have an alibi, then it's probably reasonable. But otherwise, I think I shake your hand so you turn up murdered. Does that mean because my DNA is on your hand that I must have murdered you because of some piss peak at UKHAS? But it doesn't mean sometimes what people write into it, and it's exactly the same in terms of astrobiology, right? How to make it all sterile? Well, I've got some ideas. You need to sorry. Yeah.
With the sterile thing, for the rocket, the one that I kind of recently must go onto the rocket going up as a bit of a stand there, but
yeah, I mean, the rocket is a harder, it's such a platform balloon. I'm going to pass it up.
Well, the balloon has got that high speed to stop, to make it hard for stuff to appear.
Well, of course, I wasn't relying on the hearing. I mean, that's what my mentality was. It says about 10 millibar. That's a hundredth of an atmosphere. If I have a 50 milliliter syringe and I put it out, then that is to sucking in 0.5 ml at ground level. And so I've got 0.5 ml and then I can push it into something else. And if I do that enough times, I begin to suck a meaningful amount of air. As I said, I mean, the colony forming, if you go on a petri dish, the numbers are quite low here on the ground. Adjusting for pressure, they'll be extremely low. And so that's the other reason I don't believe the numbers. And a balloon that could drift for a long distance where I really meaningful volume into it, that's probably the best way to do it. A rocket samples a very large length in a very quick amount of time, so then you probably do want to stick it to something like that. How you make the balloon, a rocket sterile, I don't know. Both for rockets and balloons, what I'm thinking in my biohacker basement, for both of them, I think peroxide is, hydrogen peroxide is the gold standard. That's again from Viking. You soak in say 3% iodine in it, and it's sterile. Not only does it not have DNA or anything alive on it, you've even broken down sort of complex organic chemicals that you might think came from something alive. So nobody soaks stuff in 3% peroxide. They just can't. When they launch a probe to Mars now, they say it's acceptable if it's got less than 100 colony forming units per metre squared, which I think is ridiculous. So we're probably inoculating Mars all the time. The Viking landers, they tried to autoclave the entire lander, including the computer. I don't think they succeeded. They tried a lot to try and make a computer you could actually autoclave in hot steam.
Temperatures we've got.
121 degrees. Well, I don't really. Autoclaving kills organisms, it doesn't kill DNA. You can get DNA from an autoclave sample. I know that. You've got to coat the I think you can't do it with latex weather balloon. Those of you who've been following what I've been discussing, I'm thinking probably of flying a solar balloon instead, because they're made of bin bags, they're made of polyethylene. You can probably find plastic that can withstand the peroxide, and then you've got, it's not, altitude's not so high, but you have a chance of completely sterilising your balloon. James?
Sorry about that. We've got a few people, the people from the States who are presenting next are ready to go. I was wondering if we could...
Okay, let's move on. Sorry. I was switching on there. Sorry. Cheers.